Hello, everyone. My name is Silvia, and today I'm going to talk to you about computational modeling of particle state in nasal drug treatments. Okay, so this work is framed within the project DREAMS, and this project, well, DREAMS stands for Particle Deposition Computational Model for Children Airways with Mucous Surface. Now, the main goal of this project is to improve the efficacy of intranasally administered drugs in children patients for the treatment of upper airway diseases. And the project splits in two parts, and today we're going to focus on the first part, whose aim is to improve the accuracy of particles deposition. Now, here's the outline of the presentation. First, I will go through the experimental results obtained by our collaborators at the University in Libre of Brussels. Then I will go through the numerical simulations, the numerical framework we use for our simulations of airflow and particles transport. I will delve into the particle deposition behavior, and at the end, there will be some conclusions and outlook. So starting with the experimental results. Now, very briefly here, just to give you the context, our collaborators at the Transfer Interfaces and Processes Group in Brussels considered a 3D printed nasal model of a 9-year-old patient, which is what we see here. And this is made up of 6 different regions, okay, which are labeled A to F. So A corresponds to the nostril region, the anterior parts of the nose. B is the olfactory region. C is the middle turbinate. D is the lower turbinate. This is the nasopharynx, and at the bottom there is the postnasal region. Now, what they did is to implant this nasal model into a spray support. We see here a side in front view, and they have then injected, using a single dose unidirectional device, they've injected solid particles. And then by imposing a constant flow rate in their spray support and injecting the particles, they have looked, using this device, they have looked at the particles deposition. Now, the particles we're injecting are ranging between 9 and 54 micrometers in diameter. The angle of injection is 17 degrees, and the mean spray velocity is 49 meters per second. So for the inlet flow rate of 15 liters per minute, they took 2 tests, and then the average of these 2, and they've looked at the particles deposition in this region A to F. And this is what we're going to refer to for our computational models, for validation of our model. Now, the numerical framework that we use for our simulation. Now, if you were here earlier on, Bear already gave us an idea, but I'll briefly mention. So from the 3D printed nasal cast that they used in the experiments, what we did is to create a 3D computational domain and a mesh, which is based on the CT scans of the real patient. So basically what we have in here is exactly the same geometry. So in our computations, we are using the same patient-specific geometry. And here is what we see. This is the mesh. So it's made of 13 million elements and 3.5 million nodes. Okay, so the fluid flow inside the airways is governed by the incompressible Navier-Stokes equations. And then by defining the differential operator and the force term, we can obtain a compact flow of the system we have to solve. And at the end, we have a solution decomposition where we have 2 different scales to solve. The grid scale, and then for the unresolved subgrid scale, we use a algebraic subgrid scale model. And so the Navier-Stokes equations are solved subject to boundary conditions. So at the inlet, we impose a constant flow rate. At the walls, we impose a no-slip boundary condition. And at the outlet, we impose a zero traction condition. Now, the simulations are run in supercomputer Mare Nostrum 5 using the in-house code ALIA, which is a finite element high-performance multi-scale multiphysics code. Now, here we're looking at the solution of the flow field. So for the inlet flow rate of 15 liters per minute, what we're seeing here on top is the temporal evolution of the magnitude of the velocity in 4 different regions across the geometry. So the 4 fixed locations. So you can see that in locations C1 to C3, so the first 3 more front ones, the solution, there is a minor transient time, and then the solution reaches a steady state, but there is minor oscillations. So we consider it as a sort of a steady state kind of solution. And whereas in the posterior region, so C4, the solution has a very oscillatory behavior. And this is in line with the nature of the flow in the posterior part, which is an unsteady nature in the pharynx region. And here below, we see the contour plots of the magnitude of the velocity. Now, for the particles transport simulation, we solve the Newton's second law, where the sum of the forces is given by the drag force and the gravitational buoyancy force. Now, in the drag force, there is the drag coefficient and the particle Reynolds number, which is a function of, depends on the relative velocity between the particle velocity and the fluid velocity. And it is what was previously computed by the fluid flow simulations. And in the gravitational buoyancy force, well, this contributes to the dynamics when there is a density difference between the particle and the fluid. Now, upon discretization, there is a Newmark scheme that with which we solve for the particle's position by integrating twice from the acceleration. All right, so now the particle deposition behavior. Now, the point here is that once the particles are in transport through the nasal cavity, they will eventually become in contact with the nasal cavity walls. Okay, so let's take a look here. If we take a slice through the nasal cavity geometry, here we have a slice. We look very closely to what happens at the wall. In our original model, what we considered was a rigid wall type of model. And this means that a particle traveling, once it becomes in contact with the wall, it deposits. Okay, so this is called the deposit on touch condition. Now, what we did is to perform our simulations, so transport and particle simulations, and we compared our deposition results, computational deposition results, with the experimental results that they had in the experiments. And here is what we have. So for the 50 liters per minute flow rate, what we see is that in the 6 different regions, well, there is quite a discrepancy between the experimental and computational results, especially we notice in the experiments, majority of particles are deposited in the olfactory regions, whereas in our case, they're deposited in the anterior part of the nose. So then we thought, how can we improve a particle interaction model to have a better deposition results, more in agreement with the experimental one? And so here, when the new model comes into place. And so instead of considering a rigid wall, we take into account that, in fact, the nasal cavity walls are not rigid walls, but they're coated or covered by a very small layer, which is the mucus layer. And it's a very complex dynamics going on in the mucus layer. So what we assume here is that instead of depositing upon touch, the particle will bounce against the wall with the criteria based on energy and rebound. So then for this particle wall interaction model, what do we need? So how can we define this accurately? How can we define this model accurate? So we need a deposition criterion, we need a new direction after bouncing, and we need a new velocity after bouncing. So starting with the first one, deposition criterion, we define a critical velocity based on the work from Ceccacci. And this critical velocity takes into account different parameters such as the mucus viscosity, the particle radius and mass, the restitution coefficient. And the idea is that if the magnitude of the velocity, of the particle is greater, it's greater than the velocity magnitude, then the particle, is greater than the critical velocity, then the particle bounces and it continues its trajectory with a new direction and a new reduced velocity. So the idea is that at each bounce, the particle loses energy until the deposition criteria is met, and in which case the particle deposits. So for the deposition criteria, we have a formula. Now, how do we determine the new direction after bouncing? Now, this is something that I've omitted earlier on, but it becomes very relevant now. And it's the fact that in the experiments, they've coated the nasal cavity, the inside walls of the nasal cavity, the 3D nasal cavity cast, with a gel simulating the mucus layer. And here was what we see here. This is the macroscopic image of this gel simulating the mucus layer. So as you can see, it's a very rough surface. So then what we did is to obtain an STL image or a CAD image of this surface, and we've characterized this surface. We did a mucus characterization. So basically, what do I mean by that? So we have considered different colliding particles against this surface with a certain diameter and an angle of attack colliding against the surface, and we have extracted the probability distribution of rebound angles. So looking at this scenario, we have the red particle that's impacting against the surface, and it will intersect one of the elements of this surface. Let's consider this red element here with this normal. And then what we do in this element is we construct a local basis, and then we can define the angles theta and phi in spherical polar coordinates and obtain these rebound angles. We repeated this for many, many particles, and so with many diameters and angle of attack. But just to give you an idea of the type of results we obtain, for example, for a colliding particle of diameter 10 micrometers and an angle of attack pi over 6, we obtain the joint probability distribution of angles theta and phi and the marginal probability distributions. So what we can see is that the histograms of the marginal probability distributions fit quite well with a Gaussian profile for angle theta and for angle phi. So then now it's the key point here is how to connect the microscopic level of the mucous surface to the organ level simulation. That's what we're doing when we do the particles transport simulations. So this is our nasal cavity geometry. And if we look closely at what happens at the wall, we'll have particles traveling and they will become in contact with a wall element in the nasal cavity. Now, this is a crucial point. In our simulation, this wall element, the blue one here in this case, it's at all effects a flat element. It contains no information on the mucus roughness, on the surface roughness of the mucus layer. So then the next step would be to try to introduce this roughness. And so we generate angles theta and phi of rebound by randomly given the distribution, the Gaussian distributions that we found. And then once we have the angles, we rotate the local basis of the nasal wall element to determine the new direction of the particle. So then in this way, we virtually reproduce the roughness of the mucous surface from the statistics. Now, for the new direction after bouncing, we have a numerical model. Now, what's the new velocity after bouncing? Okay, so for this, we can look at this diagram, which it's in 2D, but really helps understanding what's going on. So we can decompose the particle velocity into the normal component and the tangential component. And as we're assuming we need to meet the deposition criteria, we need to consider an inelastic type of bouncing. And so there will be it's a loss of energy type of rebound. And so to do this, we introduce parameters alpha n and alpha t for the velocity after the collision. And so these two parameters will vary between 0 and 1. So if they're both 0, then we are in the deposit on touch condition, which means that the velocity after rebound is 0. So the particle deposits. If they're both equal to 1, we are in the perfectly elastic condition. So then ideally these two parameters vary between 0 and 1. But what we want to know is optimize these two optimize these two parameters. And so this is what we're going to do, and it's our next step. So for this parameter study, we do a sensitivity analysis using the Dakota software, which is interfaced with Alia. And so we obtain a combination of randomly chosen parameters alpha n and alpha t as an input. Then Alia computes the particle trajectory and outputs the deposition in the 6 different regions. And then it begins again. So two new parameters, a new combination is generated, and then we obtain the deposition again. So we repeat this many, many times, and we obtain a statistical information. And just to mention that this sensitivity analysis is performed for the 15 liters per minute inlet flow rate. And this is not, okay. Now, for one case, what would happen? So just to show you how the simulations would work in our case. So particles, particles are injected. So this is the nasal spray. So particles injected, they start to travel through the nasal cavity. And you may notice, or you may have noticed, that some particles disappear from the animation. This is just a a visualization artifact, because those that disappear from the animation are actually deposited. So in the end, we obtain a particle deposition. Now we repeat this. There we go. We repeat this 500 times. So with 500 different combinations of alpha N and alpha T, we obtain the deposition results. So what we're seeing here is the particle deposition in the 6 different regions of our geometry as a function of parameters alpha N and alpha T. Now, the idea now is to extract the combination that better conveyed the experimental results. So then from here, from this distribution, we extract the alpha star, alpha N, alpha T star, let's say combination, which conveyed the smallest error. So if we look at this bar chart, we have in blue the experimental deposition results. In red, we have the results obtained with the deposit on touch condition. And then in yellow, we have our new results with our new model with these alpha N and alpha T star parameters. And so what we see is that the mean relative error in the first 4 regions was reduced almost by 5% compared to the experimental results, experimental deposition. And in particular, in the olfactory region, where we have the highest percentage of deposition, it was reduced by almost 10%. And also, as you can see, the actual distribution of the particle is quite different. So here, the deposit on touch, we see there is in the particle wall model, there is a very different type of distribution, which is in line with what they see in the experiments. Now, it's worth mentioning that in Brussels, in the experiments, they've repeated the same tests, but for a higher flow rate. So now we're looking at the 60 liters per minute flow rate case. And we proceeded in exactly the same way. So we started to observe the deposition results with the deposit on touch condition. And here's what we see again, comparing our results. Again, we noticed that there is quite a discrepancy. So then what we did is proceed in the same way. Now, computing the flow field. And well, in this case, there's a higher flow rate. So this solution is oscillatory all over the geometry. And so in this case, what we did is run a simulation, one-way coupling simulation of fluid flow and particles transport using the coefficients alpha N and alpha T star that we previously found. So using these coefficients, that's what we obtain. So again, it's exactly the same type of information, but for the new flow field. And so the mean relative error is also reduced by 10%. And in the olfactory region, we managed to obtain quite a nice agreement. All right, so then for the new velocity after bouncing, we have the alpha N and alpha T star. They should have been, but yes. And right, so this brings me now to the conclusions and outlook. So in summary, the goal was to improve the accuracy of particles deposition. We've noticed that with the deposit on touch condition, we did not get good, accurate results. And so we developed a particle wall interaction model. And we've noticed that we have high accuracy of deposition with the experimental results. Now, what's coming next is to evaluate the fate of the deposited particles. Now, without going into too much detail, this is a work in progress. But basically, in the DREAMS project, we would be moving on to part 2. And this is the aim of part 2, so evaluate the fate of deposited particles. What does that mean? Now, this is the deposition map that we have. And so if we zoom in on what we have at the macroscopic level, these are our deposited particles in the lumen, and different colors correspond to different diameters. And so then we need to consider these particles on the mucus layer. And so these particles undergo the process of dissolution, which we can model by using the Noisy-Whitney equation, and they go the process of diffusion, which we can model by the advection diffusion reaction equation. So this is work in progress and what we'll be working next. Now, I'd like to thank the team and particularly Bear, who is here in the room, and thank you all for your attention.